Here's another classic amplifier for us then. This is a Musical Fidelity A1. And this is labelled as a Class A amplifier, and we can see the whole top surface there is heatsink, and this gets pretty hot. And this is working, but there's some classic issues you get with these amplifiers, in that the volume control goes very noisy, and also the switch gets kind of temperamental. So we're not going to try and fix these items as they are. There's some modifications that we can do to this amplifier that should resolve these problems permanently, really. So that's what we're going to look at. But before we do that, before we start messing with the circuitry or adding bits or taking bits away, we want to make some baseline measurements on this thing. So that's what we'll do. And the first thing to do, I guess, is simply connect it to a scope, and we'll look at bandwidth, and we'll be able to see the effects of the noisy volume control and the like there. So let's do that. We'll connect up to a scope and see what results we get on there. So let's just look at our noisy volume control first of all. I've got a signal coming in here. If I turn up the volume, you can see it's reasonably smooth. And then you get these kind of, you see the sort of jumping effect there. That's just, you know, volume control's wrecked, and this is kind of the effect you get, which is pretty unpleasant and not really, you know, it's not really very usable like that. And then the other thing is, if you see, we've got a 5 volt per division here, and so I can get up to just about 15 volts, just touching 15 volts before you can see it goes clearly very non-linear there, so we're distorting very badly up at that point. That's just an RMS voltage of just over 10 volts there. So we're getting sort of 10-12 watts of this thing before it really goes kind of off the plot. So it's not a high power amplifier. This is not for your rock music or whatever, but you see the effect of the volume control there. It's terrible. But obviously the Class A has got a reputation, comes with a particular sound that is actually very pleasant. So anyway, that's our volume control problems. And we'll make a bandwidth measurement on this before we start to do some particular measurements on distortion and things like that. In actual fact, we can, on these modern scopes, we can do a frequency response plot quite readily. So I'm just going to set that up now, and we'll run that measurement. Right, so we're set up to make a frequency response measurement, and if I just start that measurement, what's happening here is the scope's just gone through. There's a generator built into these scopes, and it just goes through different frequencies and measures the level on the 2 channels, and then comes up with a plot for that. So it takes a little while to run, depending on how many points you're using, but then you get a useful graph. You can see the graph, it's starting to draw the graph as we're going through the different measurements here. Now there's other ways of doing this. You know, you can do this manually, or you can use the audio analyzer, but it's just convenient when we're here to use this. So I'll let that finish, and then we'll pick up when it's got the final result. Here's the final plot then, and shows us we've got about 26 dB again at 1 kHz there, and phase is flat there. So I've got this set to 1 watt in output. This is where I'm making the measurement here. It's a 1 watt output. So if I increase my marker here until we reach 23 dB again, then that's going to tell us our bandwidth really. And we're up there, just about 100 kHz exactly. Phase has gone off a lot more. It's down to be 85 degrees. But there we go. So we've got about 100 kHz of bandwidth, say, and that's fine. So we'll use that as a reference. I'll take this plot, keep it aside, and then we'll just check on this when we've done all our mods. Don't expect to see any change in this. This is just kind of housekeeping, making sure we've got a record of everything before and after. The real thing we're going to see here is the change in the behaviour of these controls, and we're also going to see some positive benefit on the actual noise output of this amplifier. So let's say we've still got some measurements to make, so we'll go now and we'll look at the actual noise, and we'll look at the distortion. So just before we finish with the scope measurements, then we can make a rough noise measurement on this, or we could make an accurate noise measurement if we were looking to do that, but I'll do that on the audio analyzer. But this is very visual, of course, and at the moment we're seeing sort of 6 or 7 millivolts of peak-to-peak noise, and this is at 0 volume. So this is the hiss that you hear in your loudspeaker when there's no music. And then if we turn the volume up, you can see that the noise increases dramatically with the volume control. That's at maximum there, and we're peaking sort of 15 millivolts peak to peak there. So you're going to hear a definite hiss through your loudspeakers when you're playing at high levels here, or when the level's set high. So that's obviously not very pleasant, and I think we can do a bit better than that. So we'll go and repeat that measurement on the audio analyzer, and we'll also look at the distortion. Alright, so here we are connected to the audio analyzer, and so we can see our spectrum. But first of all, let's look at this number here. So this is our RMS noise. So we looked on the scope there, we looked at peak to peak noise, but this is the RMS noise, and so we're reading 600 microvolts, and this is with a volume at minimum, and I've got no signal going in. So if I turn my volume up, if you look at the graph, the noise floor in the graph is rising, and we see that this RMS noise is going up as well, and so we're up just over 2 millivolts RMS there, where we saw 15 millivolts peak to peak on the scope, and you can see the peak of the noise floor there is hitting about the -90 on the spectrum plot. And if we turn the volume back down, we're sort of about -120. So we've got about a 30 dB increase in the noise floor over the whole bandwidth, and that results in this sort of high levels of what you're going to experience as hiss through your loudspeakers. So we'll use those two numbers as our noise reference. So it's 600 millivolts volume minimum and 2 millivolts volume at the maximum. So then if we go and look at this graph, actually it's quite interesting. We see here's our 50 Hertz, so this is just some power supply ripple down about -85, and we see that the second harmonic, the 100 Hertz from the mains, is much more dominant. It's up about 65, and there's further harmonics here, so this is a bit messy. Now this could be just down to some of the capacitors having aged, so we'll see. We'll obviously look at replacing them as well, but hopefully when we do that kind of basic stuff, the basic sort of service stuff, depending on how the circuitry in this amplifier works, hopefully we might see these levels drop. Now if I turn the signal on, this is volume at minimum, so we've got some leakage there where we see about 4 millivolts of and this is actually the volume control bouncing around. Yep, so there's a sort of that's just our leakage at 0 level, so we're down about -65. And if we turn the volume up, if I turn the volume up to sort of about 2.6 volts RMS, that's about 1 watt. So that's about 1 watt output there. And we can see that so we're almost +10 on the fundamental, and then about -60 here. So we've got about sort of 65-70 dB of harmonic distortion. But we also see that this 100 Hertz here, it shows as sidebands on the fundamental, and it's also beginning to show in the harmonics as well. And if we go and make a THDN ratio measurement there, we're reading about 0.038. So that's at 1 watt, we're reading 0.038. So that's 68 dB THDN. I tend to relate to dBs more than percentage, so that's why I click to that. Anyway, let's try a higher level. So if we go up to about 8.9 volts, just under 9 volts, that's about 10 watts, and you can really see the sidebands from this 100 Hertz coming into play there. That's really pretty horrible. And we can see, if we look at the distortion again, we're about 52 dB there, and in percentage 0.24%, so I've got about 1/4% distortion at pretty much full level here, and we can't really go any much further than this. If I go any further, the distortion's just going up, and we're really starting to clip. As you look at the spectrum there, it's absolutely horrible. And it's not just the harmonics, the sidebands from that 100 Hertz is really dominant there. So hopefully that'll improve somewhat when we change our capacitors. But we're hoping that also the other circuitry changes we make is going to fix these noise levels that we saw. So let's take a look at what we're going to do. So these amplifiers were very well regarded in the day. Back in 1984, these were in production, and so you find that there is quite a bunch of information online about them. And this page by Mark Hennessy is quite complete, and I've spoken to Mark. He's happy for me to share the content here, and what he's got is you know, an introduction, just some of the history, and then some of the comments about the issues and the like, and we start right away by talking about reliability being an issue. So the first page is about the history and the like, and then we go on to the second page where he takes the thing apart, and we've done some reverse engineering here, and he talks about the problems that we are experiencing, that being, see if we can find it, yes, here it's here in the line preamp, and so here's the statement here, which essentially describes what we are seeing. The volume controls and input switches get very noisy very quickly, and he's saying he noticed this problem just within a few months, and you know, there are design issues here based on what he's reverse engineered. And I think here's a statement from one of the designers, and I think there was some sort of engineering compromises that were forced at the time that has caused some issues here. And so the kind of conclusion here is, if we go and replace the volume control and the switches, the problem is just going to reappear quite soon. So we need to take further steps. And if we go on to the third page of this story here, what Mark's done is he's come up with a replacement for the input stage, and it's a fairly standard op-amp circuit, fairly sensible circuit. So without me going and reverse engineering things and you know, trying to figure out the best direction, I'm simply going to copy what's happened here. It seems there's a bunch of people done this and had good results. So this is what we're going to do. We're going to replace the front end volume control with this circuitry or something very similar, and then we'll also replace the switch. So here's some pictures of the sort of modified board that Mark did, and then if we go down, we can see there's some options for changing the input selector. So we'll look at what parts are available and try and find something sensible for that. So this is what we're going to do. As I say, I'm not going to try and really you know, get into the deep detailed design myself, because it's just very time consuming, and there's really no point. Someone else has done it, and you know, everything I read here is all pretty sensible. The thing that's missing here though is results. We don't have any spectrum plots or plots of the noise or any distortion, any of that kind of thing. So that's what we're going to add once we've done these modifications, and we'll see. We should see the numbers should tell us that things are going in the right direction. Next thing I'm going to do then is we'll open up the unit and have a wee look inside, and we'll order up some parts to go and make these modifications. Here we are looking inside then, and it's nice and clean enough actually. Straightforward enough layout. We've got our power supply on here. Here's our phono preamp, and then this is our input. They call it a preamp, but really that's our input gain setting. And then we've got our two power amps, one on either side of the heatsink here, and then of course the main top heatsink secures onto this with a conductive paste all the way along there. And then this is our input selector. I've already taken the shaft out of there. So let's take a look at. We'll take a look at this a wee bit closer, and this is the input selector switch, and we can see that the actual metal body of this thing, there's some movement in that, and you can actually see the contact in there moving around. So that's obviously not going to give us a very reliable connection. Now I could look at tightening up this frame, this metal frame around the switch, but I just don't think it's worth it. You know, we're going to do that and then have unknown results. So the right answer there is to just change that, change the switch for something more robust. Right, so we're starting to take this amplifier apart now to make our modifications, and this is the PCB from the switch, and we saw the mechanical issues, but we can also see it's very tarnished here. And again, we could clean that up, but it's just going to give us questionable reliability over time. So it's time for this guy to go. And I have received some parts for this amplifier, and I bought this switch here, which is a decent quality switch, and I spent 17–18 pounds on this guy. But what I realise as well is that this has also got the contacts exposed, and it's just going to have a similar issue over time. Now I don't know, it'll be in the data sheet what the life expectancy of this thing is, but I'm just a bit hesitant to use this given the exposed contacts. So what I'm going to do is use one of these guys, much cheaper switch. So it kind of goes against the grain to sort of downgrade in that way, but I think for this application it's going to be just fine. And I know how these are constructed inside, so I'm fairly comfortable it's going to be a good answer. And of course everything's enclosed, so we've not got that problem of the contacts being exposed to the environment so much. So I've got this little bracket here that will mount the switch on, and that will then get screwed to the PCB, and then will connect to the main shaft as the previous one did. So that's our input selector, and then I got the volume control, very nice quality Born's volume control here, and I've made this little PCB with the amplifier on it, and so that will just mount into the existing position, and we'll wire it into the board. So I'll take a close up of this, but that's us. So we'll get on now and start to install some of this stuff and see how we go on. Alright, so before we get carried away and put all this stuff together, we should check the performance of our little amplifier module with the volume control. So we're connected up to the audio analyzer here and looking at the spectrum. So if I turn the power on, then this is our noise floor, and we're doing about 140, and we can see we've got some 50 Hz and we've got some harmonics of that, and So it's essentially, there's a very little bit of power supply ripple there. But if we look at the voltage, we're down about 8 microvolts, and this is with no signal going in. So if I turn up the volume to maximum, we're seeing a bit more of that ripple on the supplies there. Supplies are just not super clean, and we're up to about 16 microvolts on the actual levels. But this is still, these are tiny levels now compared to what we've seen before. And if I go then, and this is still at maximum volume, if I go and put my signal on, got a very clean signal there. And let's then go and look at our THDN, and we're down at 0.001, and if we convert that into dB, nearly 100 dB, and I'm pretty happy with that. Given the op amp we're using, and given the currents that we're using in the feedback of the op amp, I'm quite happy with that, and it's significantly better than the amplifier itself. So it's just not gonna be seen at all, you know. The amplifier is going to dominate. So that's all good then. We're quite happy that our amplifier's working well, or our volume control section anyway. So we'll go and integrate that into the main amplifier then, and continue with our measurements. Here's all our modifications done then. So we've installed the new selector switch there, and that's all working just fine. Nice sort of positive action on that, so I'm quite happy with the performance of that switch. And then we've installed our sort of front end amplifier volume control board. Changed a bunch of capacitors on the power amp side. There was some that were, you know, the ESR was a bit high. They weren't particularly bad, but just worth changing anyway. So I commented earlier when we looked at the spectrum plots that maybe some dry capacitors were the reason for the sort of high 100 Hz and some of the harmonics of that. But then I thought about it a bit more, and really my conclusion is that that's just basically the Class A operation. You've got an inherently high bias, and therefore you're pulling a bunch of current from your reservoir capacitors. So what I've done here, just to try and push this in the right direction, is I've changed there was two capacitors here. There's one that's connected straight to the bridge, and then we've got a series resistor and then another capacitor, and I've taken out that one and replaced it with these higher value capacitors. So it was a 10 millifarad before, and these are 33 millifarad, and it just so happened I had these available. And they're only 25 volts, which for a lot of jobs is just not high enough, but it's absolutely perfect for this. A little bit higher would be good, but it was 25 volt capacitor that came out, so I'm fairly happy with that. And the rail only goes to about 21 when I measured it. So that's us all together then, and so let's now go and we'll make some measurements of the complete unit. Here we are after our changes then, and we're connected to the scope just to show the behaviour of the volume control, and I'm just moving it up and down there, and you can see it's moving very smoothly. There's no crackling, no jumpy bits. And if I then change to a different input, so we're clicking the input selector, again it's a very clean transition. There's no sort of jumps or bumps or any horrible stuff going on there. So that's all good. Let's then we'll take a look at the noise output minimum and maximum volumes. So if we drop down to 5 millivolts a division, that's where we were before, and we can see our residual output there, and we've got about 2 or 3 millivolts peak to peak, and this is again, it's a wide band measurement here, so there's other influences other than what the audio analyzer is going to see and what you might hear. Anyway, this was about 7 millivolts before we did anything, so there's a reduction, you know, like by like there's a reduction. And this is at minimum volume. If I turn the volume up to the maximum, and that's me at maximum there, and there's really no change whatsoever on that plot there. So this is now a very quiet amplifier. So all good. Alright, I'm going to go and then I'll just make the frequency response measurement as we did before, and we'll then connect to the audio analyzer and look at the measurements in more detail. So everyone's back together then, the amp's running here and we're looking at the output. There's no input connected, 8 ohm load in the output, and what we're seeing here is we've got about 260 microvolts of noise on the output, and if we look at the spectrum, the actual noise floor itself is not much different than it was before we done these changes. What we find is that there's a reduction in the power supply ripple components there, just due to those increased value reservoir capacitors we put in. So if we then turn our volume up to the maximum, that says at maximum there, so we're reading about 380 microvolts on the output, and before we done these changes we were about 2 millivolts. So this is a very big change here, and again I think this is mostly dominated by the power supply ripple components there. It's not so much absolute noise floor on the thing. So there we are. We'll turn our volume back down and we'll put a signal on, and I suppose the first thing to see there is that the volume increases quite happily. It's not bouncing all around the place like it was before. So if we go up to about 2.6 volts ish, that's about 1 watt, and let's have a look at our THDN. So we're about minus 70. I think we've got a couple of dBs improvement on what we had before. That's about 0.03%. But the you know, it's the second harmonic that dominates this thing. It's not so much noise floor or these other components. And I think we've just got a little bit of improvement because these other components have reduced, but it's not dramatic because second harmonic dominates. Let's then go to 10 watts in the output, which is about 8.9 volts. That's close enough. Okay. And again look at THDN, and we're about 0.25%, which is where we were before. And in dB, minus 52 is what we had before. So that's everything we were gonna do. I think we'll just look at side-by-side comparison before we wrap up here. So let's look at some before and after results side by side then. And the first one I'm showing here is the power rail ripple, and this is where before we did anything we had the 10 millifarad capacitor on the supply rails, and we've got about it's 100 millivolts of division here, so there's about 350 millivolts of ripple there, and then after we make our changes to the bigger capacitor we're down probably about 150. So we've kind of, you could say we've halved the amount of supply, the rail ripple there, and that's what shows up in our spectrum plots. This next one was the bandwidth then, and you know, the gain in the front end stage is different, and I've got different levels. I should have had a consistent level, but unfortunately not. But what we see is the bandwidth's the same. It's 100 kilohertz, even though I've got a different gain there. The bandwidth's consistent 100 kilohertz, and the phase is not changed either. So what that tells us is that the little front end amplifier volume control board, it just doesn't have any effect in this sense at all, which is again what we'd expect. So here's our output at minimum volume before and after, and you can see here that the actual noise floor is pretty much the same, and the main difference is if we look at this 100 Hertz component, it's about 65 here, whereas we're near, you know, we're maybe about 74 or something there, and then at your 200 Hertz we're down about -90 as opposed to 80 before. So these components are the thing that's really affecting the noise floor in this case. However, when we look at the maximum volume, it's very clear there's a distinct difference in the noise floor levels here, and these levels don't change, kind of thing. They're consistent with what we saw in the previous plot. So we've still got the benefit here of reduced 100 Hertz, reduced 200 Hertz, but we've also got a considerable benefit here with the lower level noise floor, and it's about 25 dB lower, which is 18 times. Here's a harmonic distortion, just with 1 watt output, and we see a very small difference there. Just a couple of dBs, and that again comes from really just the reduction in the 100 Hertz, 200 Hertz, and on the sidebands around the audio. If we look at the sidebands there, they're about maybe 84, and then in this case we're about maybe 93, something like that. So there's almost a 10 dB improvement in the junk around the audio there, and you can't even see the sidebands on the second harmonic of the audio, whereas they're quite present in the before plot. And the noise floor here, why is it not showing high? Well, that's because we're just because of the input level we had, and the fact that the volume control is not fully up. I should probably have done this test with a lower level input signal, and then we would have turned the volume up, and we would have seen the noise floor there. And the last one's just at 10 watts, and these are essentially, in terms of harmonic distortion, they're pretty well identical, and that's because the second and third harmonic, they're dominating this measurement now. But again, when we look at the sidebands around the audio, we're about 75 in the after plot, and we're about 65 before, so that we've still got that 10 dB improvement there, which is no bad thing. So as a conclusion then, what we're saying is that we've got a far quieter amplifier, and essentially we've not affected any other parameter. So we've got a quieter amplifier, more reliable volume control, clean volume control, and a clean selector switch. So that's really us, and I think the only thing now to do is we'll go and play some music, have a listen to how this thing sounds. Alright, here's our A1 after all our changes there. And so this was a nice amplifier before we'd done any of this. Nice sounding amplifier anyway. So let's just see how it sounds now after we've done all this.